Thank you for the introduction, and special thanks to Paul and Marike for inviting us to this webinar series to present our FracTex plugin. In the following 15 to 20 minutes, I'm going to talk about the FracTex plugin itself, its development and its applications. In this presentation, I will first give you an overview about FracTex, where the name comes from and what it's about, the basics about the grade level co-occurrence matrix, then the extension of the given workflow from 2D to 3D and to using more directions than 13. Later on, I'm going to talk about the directionality of the grade level co-occurrence matrix, which led to the development of the FracTex plugin. And finally, I'm going to talk about the parameters used for the computation in OpendTect. FracTex stands for fracture detection using textural attributes. And in this algorithm, we compute the grade level co-occurrence matrix in different directions. We then compare these different results. And based on this comparison, we can derive a factor for the spatial variation within our seismic data. And we can also determine a direction with the most variability. This output can then be used to determine fracture zones, or we can use it to describe different seismic facies. The grade level co-occurrence matrix, or short GLCM, is an image processing method developed in the 1970s. And it basically describes how different combinations of pixel brightness values occur in an image. Usually, we are using neighboring pixel values, but the distance between these pixel values can also be of higher order. In seismic interpretation, it is commonly used to describe seismic facies or to highlight geomorphological features. To understand the basic ideas of the GLCM calculation, I created a simple 2D image. So on the left side, you see a seismic amplitude cube already converted into gray levels. So in this case, we have light gray to dark gray or black colors. The light gray colors are represented in the middle column with a value of 1, and the black colors are represented with an 8. After this conversion to a gray level cube, we determine the number of co-occurrences of pixel neighbors, and we insert these co-occurrences in this co-occurrence matrix on the right side. This procedure can be done in different directions, and I will now show you an example for doing this procedure from left to right. So in the first case, we have on the top left a 3 next to 1. So we put the coherence of 1 into our co-occurrence matrix. The next point would be 1 next to 3, which comes in the upper line. Then we have a 3 next to 4, 4 next to 5, and so on. So we continue this procedure for a whole seismic image and insert this in our matrix. The GLCM method is a symmetrical method. This means that if we do the comparison from left to right, we also have to do it from right to left. So you can either compute this line by line or sample by sample, or you can simply take the existing co-occurrence matrix and mirror it on the diagonal and add it to the existing co-occurrence matrix, which will then give these results. So on the right side, you have now the final GLCM matrix with all co-occurrences. And in this case, we have the most often an 1 next to an 1, which is 18 times. And some of the co-occurrences doesn't happen at all in this image. For further calculation, it is now necessary to create a kind of probability matrix. This probability matrix is created by dividing each matrix entry by the total sum of matrix entries. So in this case, the result will be like this. And we have a probability of having a 1 next to 1 of 21%. And for example, we have to have a 4 next to a 3 would be 2%. Based on this probability matrix, we can then further compute other attributes. Of course, this computation can also be done in other directions. So I'm just showing you the results and not each step of this computation. In the upper line, we have the calculation in the vertical direction. Below that, we have one diagonal computation. Then we have another diagonal computation. And finally, we have a computation where we use all directions at once. So it's simply an adding of all these individual matrix entries to get this kind of average matrix. And based on that, you can then compute different GLCM-based attributes. These GLCM-based attributes can be grouped into different attribute groups. The first would be the contrast group. In this contrast group, we have attributes such as contrast or dissimilarity. And this contrast group is basically a measurement which is depending on the distance of the GLCM diagonal. Then we have the orderliness group. This is a measurement how organized our GLCM is. And in this group, we have attributes such as angular second moment, the entropy, or the energy. And then we have the final group, which is the statistics group. And this is standard statistical parameters computed from the GLCM, like the mean or a correlation factor or standard deviation. In the previous example, we used a 2D image to demonstrate how the GLCM computation works. We're now extending our workflow to the third dimension, which also needs a three-dimensional analysis window. In this case, I'm representing this three-dimensional analysis window with a Rubik cube. If I open up this Rubik cube, I see this red cell in the middle. This red cell is the turning point of the Rubik cube. And in our case, for seismic data, this would be the cell where I would assign all attribute computations to. If I take a step out of 1, which would be the case in this example, this red cell has 26 neighbors, and these 26 neighbors are aligned in 13 space directions. If I increase the step out to, let's say, 2, then I have 49 directions I can do the computation to. If I increase it to 3, it would be 109, and for a step out of 4, it would be 193. In this image, I'm showing a top view of a seismic dataset with inline and crossline numbers, and the red cell would always be my center point where we'll do the computation to, and from left to right, I'm increasing the step out. In this example from the Werner Basin, we see a channel system interpreted on a coherence time slice. And in the background, we have GLCM-based energy computations in 13 space directions individually. In all of these GLCM-based energy attributes, we can clearly see the channel interiors, but the absolute value of the GLCM-based energy differs from image to image. Based on this observation, we developed a workflow which led to the FracTex attribute. In this workflow, we determine for each sample point the minimum and maximum values, and from that we compute a factor for the spatial variation, and we can also determine the direction of maximum variability. In the FracTex plugin, we have to set a couple of parameters in order to run the computation. First of all, we have to define the number of gray levels. This number of gray levels can be any number you want to, but typically we use values between 16 or 64. Then we have to define the amplitude range for the gray level transformation, and also to define the transformation method, which can be, in our case, either linear, exponential, logarithmic, sigmoid, or logit. Then we have to define the number of directions used in our case. Depending on this number of directions, also the size of the analysis window has to be adjusted. And finally, we have to define the type of GLCM-based attribute used in the computation. For a better understanding of these computation parameters, I will now switch over to OpendTect and show the plugin in a live demo. In this live demo, I'm using the F3 dataset and an interpreted base tertiary horizon. In this base tertiary horizon, we have fractured zones in the southwestern area. And for this area, I will show you a couple of attribute results using the FracTex plugin. To access the FracTex plugin, you can either use the standard Seismic Attribute button, or you can access it via this FracTex plugin button. The FracTex plugin itself is separated in two sets of parameters. So we have these common sets of parameters in the upper sections, and we have the advanced settings in the lower section. In the common sections, we have the input data, which could be any kind of seismic data. Then we have the number of grade levels. We have the minimum and maximum of the input data used for the grade level transformation, the number of directions, the analysis window, the attribute selection, the grade level transformation, and the output. The grade level can be any kind of number between 16 and 1000. You can either type it in here directly, or you can use these up and down buttons. For the minimum and maximum of the input data, you can also type in a number you want, but you can also use this show histogram button to create a histogram of the input seismic data. And in here you see this red line and this blue line, which represents the current maximum and minimum input data. So everything left of this red line would get a grade level of 1, and in this case, everything right of this blue line would get a grade level of 64. You can simply change the ranges by clicking on these buttons or typing in here. For the number of directions, you can choose between 13, 49, 109, and 193. With this option, also the computation time increases rapidly with higher numbers. For the analysis window, I recommend to use for the horizontal search window always the lowest number possible. So in the case of 13 space directions, this would be plus minus 1. If I use 49, the lowest possible would be plus minus 2. For the vertical search window, you can also change it directly here, or you can use this show variogram button, which computes a semi-variogram in a specific time interval. So in this case, it would be 924. We change it to 1600, which would be in the vicinity of this base tertiary horizon, and press the run button, and then it computes this semi-variogram. And for this data set and this depth, and using these other parameters, the optimum vertical search window would be plus minus 3. For the attribute selection, you can select between energy, contrast, inverse difference moment, entropy, difference entropy, homogeneity, maximum probability, or dissimilarity. For the grade level transformation, you can switch between linear, logarithmic, exponential, sigmoid, logit. And for the output, you can choose between the anisotropy factor or fracture dip azimuth. In addition to that, you can also steer the computation, but on the cost of the computation time. So in the following, I'm going to show you a couple of examples of the computation. So in this first case, this would be the energy attribute, where all these dark colored zones indicate areas with a higher spatial variation factor, which might correlate with fracturing. If I do the computation with another attribute with the same other parameters, the computations will differ a little bit depending on the type of attribute. So in this case, I'm also showing the energy, the entropy attribute, which gives a little bit different image. It's focusing more on this center part where all the fracturing happens and neglecting everything outside, like the energy attribute. In the following, I'm also showing the difference between the different number of directions. So this would be the same attribute, the entropy, using 13 space direction. If I now increase it to 49 directions, I'm focusing more on larger structures, and the image gets similar to the energy attribute actually. And if I'm increasing it to 109 directions, I get an even smoother image. So for the number of directions used, my recommendation is to start with the 13 space directions, as this is also the fastest computation. And only depending on the type of structure you want to investigate, use higher number of fractures. In this case, we have on the right side a salt structure. And if I take this salt structure, it is better illuminated with the higher number of gray levels, number of directions. So if I go back to the center area again, and now show you the difference between the transformation methods. So in this case, I'm using a linear transformation method, as in the cases before. If I now use an exponential transformation factor, I get a wider spread distribution of higher spatial variation factor. If I use the logarithmic, it's reducing again, and the sigmoid is again reducing again and more similar to the entropy. For the type of gray level transformation, this greatly depends on the type of amplitudes you're using. So in this case, we have a high amplitude reflection. If you're close to zero crossing, or if you have low amplitude values, methods such as sigmoid or logarithmic might work better. Okay, with this, I will now switch back to my presentation, show a couple of more slides, and then another example from the T-Bot Dome dataset. So we already talked about the numbers of directions before. In the upper line, I'm showing the standard case for the FracTex computation, where we use 13, 49, and so on directions. And in the lower row, I'm showing our new focus computation algorithm, which will be in the upcoming release of the FracTex plugin. In this case, we do the computation first in 13 space directions and determine the maximum and minimum attribute results, and also memorize the cell the maximum and minimum occur in. Then for the higher direction computations, we only use cells that are neighboring these cells with the highest or lowest values. So in this case, for the 49 directions, we can reduce to around 21 directions, depending on the position where the first result was. And the effect is even higher for, let's say, 193 directions, where we can reduce the computation to around 40 directions instead of 193, which has a great effect on the computation times. And another thing I haven't shown yet is the rows diagram that we included in our FracTex plugin. This is an example for the T-Bot Dome dataset for the 10-slip formation. So on the left side, you see the results of an FMI interpretation. And the middle columns represent FracTex attributes. And on the right side, there is the result of another so-called spectral edge attribute described in an interpretation paper. With our plugin, we get for some of the attributes, quite good match, like for the energy or the entropy attribute. For other attributes, such as variance or the contrast in some cases, the attributes differ. So in this case, my recommendation is to do this rows diagram analysis for each section or for each interval separately, and then choose the best performing attribute in this case. And with that, I will now go to another live demo using the T-Bot Dome dataset, and I will show you the results of this rows diagram computation in the live demo. In the Typodome dataset, we have the fractured 10-slip B formation, which I will show you now, and I will do the fracture azimuth computations for. So again, we access our FracTex plugin using this FracTex button. And if I'm now going into my advanced settings and I select the fracture dip azimuth, I also get this option to use show rows diagrams. So if I click on this button, then I can select the well I want to investigate. In this case, I'm using this well. And then I have to select the type of log I want to use. And then the FracTex plugin produces me rows diagrams for our attribute and also for the for FMI log. So in this case, it's by default always showing the complete range of the well. We can now change this to a manual number using, I'm sorry, I have to change the feed. So I can type in anything I want to and have to press the refresh button, and then it produces me the attribute output just for a specific depth range. Or I can use the well top information that we have. So in this case, I'm using 10-slip A to 10-slip E. Click on the refresh button again, and I get a comparison of the results of our attribute and the results of the FMI attribute. Our attribute can, in this case, because it's using only 13 space directions, can only be sampled in 45 degrees. So we have less resolution than the FMI attribute. And depending, as said before, depending on the type of attribute, we might get different results. So in this case, I'm showing the energy attribute. Now switching over to the inverse difference moment, which shows a complete different result and which I wouldn't use in this case. If I go to the attribute, it's more or less the same, so a little bit tilted in comparison to the energy, but still it matches quite well the FMI interpretation. Furthermore, you have in this options, if you choose the fracture dip azimuth as threshold value, by default it's 1, so this means it takes all the data. And I have an extreme case where I used the threshold with a set number of 3. This threshold value means that the algorithm computes in the background the spatial variation factor, and if the spatial variation factor is below a value of 3 in this case, then it will set the output to undefined. So with this, you can then highlight only areas with higher fracture rates. And the result for this azimuth computation would be now this. To perfectly visualize the output, you have to change the texture display options to classification so that you show the real numbers and not interpolated numbers. And so in this case, I'm showing values between 0 degrees and 360 degrees. The algorithm corrects the output attributes for the orientation of the seismic input data. And if I'm now switching over to the same computation with a threshold of 3, we get undefined values everywhere where we have a lower spatial variation factor. So with this, we are highlighting only areas with higher fracture density. And with this, I'm coming to the end of my presentation. Thank you for watching this live demo, and also once more thanks to DGP for the opportunity to give this presentation. Thank you.